Hi, this is Roger from Kanka Labs, today with part 2 of the video series about selecting a better multimeter, especially for hobbyists' use in the range of 50 euros or dollars upwards. Now before we start today with volts, amps, ohms and continuity testing, just some remarks. So this video series is not a review of one of the multimeters, even not of the EEV block one, even though in the end, as I already told you in the first part, I think there is no better multimeter on the market today in the $200 or euros range than the 121GW, especially concerning the features that are built in and that you don't find often or at all at any other multimeter, and that were born out of the practice of Dave Jones', I don't know, 30 years plus electronics experience. So this video series is more intended to be a kind of buyer's guide just for those who want to upgrade their multimeter collection, especially if you are working until now with a low-end multimeter and you don't know what useful features there really are in better multimeters. This video series is for you, and for the others, if you don't like it, don't watch it. So we will not start with the volts, ohms and amps measurement issues, but with what I think is the single most important measurement function that you simply need the most often in test and repair work, and that is the continuity test. Now, the traditional test for a good continuity is, first of all, there's one thing: the beeper has, of course, to be loud enough, because quite often you have some noise in the lab, and if you have a low volume continuity beeper, you just cannot work with this function. And if at one time or another you start to get angry about your multimeter because, for example, you can't hear the beeper, then it's time to upgrade. And the traditional test is just this here, just to quickly brush or sweep with the two probes. And what you can hear here, the old Metex one, it's quite loud. You won't hear it on the video in the full volume simply because the microphone is near my mouth and doesn't record ambient noises or ambient sounds as loud as they are to your ears. But believe me, this one is the loudest. And what you can also hear is that when we only get a short contact, then the beeper doesn't latch, so it gives its sound output only for the time that the continuity really is present. So this is a so-called non-latching continuity test, but it's loud enough and it records every time, however fast I'm sweeping here over the contacts. Second is the X-Tech, and what you could see, although these probes that I prefer are not gold plated, there is no problem in recording even very short contacts. Now the X-Tech has gold plated contacts and it's much lower volume, nearly as low that I would say, well, this is just the absolute minimum that I would say is acceptable. And you also can hear it catches even very short continuity, but it's also non-latching because the sound is very short, but still workable. Now let's go over to the EEV block one. And you can see sometimes it does not catch the continuity. And I wouldn't have expected that, especially from Dave Jones' experience, because this is the traditional test he always does with every multimeter, and that his own conceived multimeter doesn't pass this test 100%. I wouldn't have expected. But what you can hear is that this is a latching continuity test. Even if I have a very short contact, the sound is held for a few dozen milliseconds, but not always. So anyway, I would give all three of them an okay. None of them is perfect, but there are two or three things in any continuity test function that I have worked with that I find could be improved, and therefore let's connect my RLC box to the multimeters, and I will return in a second. So I've now connected my RLC box with the input of the multimeter and just checking at what resistance the continuity sets in. We're now at 100 ohms and going down in steps of the E12 series to 68 ohms. Although it displays here millivolts, you can interpret this as ohms, 33. And now at 22 we're having continuity. So the continuity sets in between 33 and 22 ohms. Now imagine you're measuring a transformer winding. This could be a shorted winding or a working winding. So let's say your continuity tester beeps, but what conclusion can you draw from that? You only know that the resistance is somewhere in the range of 25 ohms or lower. But you cannot decide if this is a short or a correct transformer winding. You have to look at the display to differentiate between a short, which would be near 0 ohms, and a resistance that you're measuring. So my idea is, why don't they modulate the frequency of the beeper just with a measured resistance? Then you could deduct simply from the sound if this is a high resistance or if it's near 0 ohms, and you wouldn't have to look at the display to find out the true resistance. The other way around would be if you could set the threshold resistance where the continuity is displayed or signaled by the piezo buzzer. So let's try the X-Tech with the same. Let's start at 100 ohms. Aha, here we already have continuity between 100 and 68 ohms. So this is quite on the high side. So the continuity could already be signaled if you're measuring simply a normal resistor, which is not shorted. And again, you have to look at the display to decide, is there a real short or are you measuring a component simply with its resistance? Now let's go over to the EV block 121GW, and we're now at, okay, we have some reflections here. We're now at 100 ohms, 68 ohms, 48 or 47, and continuity sets in somewhere between 47 and 33 ohm. Oh, no, it's not beeping. Okay, well, let's call this 33 ohm is apparently the threshold resistance. But the EV block multimeter has two nice features for the continuity mode. First of all, you have a selectable threshold. At the moment it's set at 30 ohms, but you can also set this to 300 ohms in the setup menu, and you can change from continuity test to cable break testing mode, which means then the beeping is reversed. If you have open leads, you have a beep, and only when it detects a short, the beep starts. So that's quite nice to find cable breaks. Then you usually continually clip or clamp the test leads to, for example, a cable or a PCB trace or whatever. And then, for example, you bend the cable or the PCB to find out where or if there is a cable breakage or a PCB trace that has broken and has only intermittent contact. So I'm now in the setup mode, and you can see here we can change between the two different modes, down or up, and 300 or 30 ohms. So that's quite a nice feature. I would have even preferred if the threshold resistance could be set arbitrarily, even to something like 5 ohms or 1 ohms or something like that. But anyway, better than the other multimeters that you have also the cable break testing and have at least 2 selectable threshold resistances. And another feature I miss on every multimeter is additional to the piezo buzzer that you have a very bright LED where the blinking frequency could also display the range of the resistance that you measure in continuity mode. That is because sometimes the noise surrounding you is so loud that even with a loud beeper or buzzer you simply can't or can barely hear it, and a flashing LED you even see when you don't directly look at the multimeter would be a great addition to that. Okay, that shall be it for the continuity test, and now let's go directly over to the resistance measurement. So basically there are 2 things important to know about in resistance mode, and that is the lowest resolve digit. Well, here at the Metex the lowest range is 200 ohms, which translates to a resolution of 10 milliohms. With the X-Tech it's the same, we have 10 milliohms resolution, but with the EEV block we have 1 milliohms resolution, and that is quite helpful when you're trying to find any shorts. Then you need this 1 milliohms resolution. It is not so much about the accuracy here, simply because the contact resistance is always a few milliohms at best. But you can cancel this out simply with another important feature, with the relative button, and now you can trace out where a short has happened on your PCB or whatever. Relative function is also present here, but here the old ones, they simply didn't have a relative button or functionality, simply because there is a fixed chipset, and any functions that are not integrated in the Interseal chipset you either could not, or only with a lot of additional circuitry, realize. While these two, there are of course microcontrollers working inside them, and you can realize a lot of functions simply by software. So the second thing about the resistance mode is what is the highest resistance you can measure. Here it's 20 megohms. Here, because we have 50,000 counts, it's 50 megohms. And the same is here, 50 megohms is the upper limit, which is for 99.9% of all measurements sufficient. But if you're working with high voltage circuits, there are sometimes resistors in the hundreds of megohms or even gigohms, but therefore you need a specialized gigohm or teraohm multimeters, which works usually from a different principle than the way how resistance is measured here. So that shall be it for continuity and resistance measurement, and now let's go over to volts and amps. So the first thing to know about the features concerning voltage measurement is what is the resolution that we get. We already had this in the first part of the video series here with the old Metex one. The lowest range is 200 millivolts, and you can see the least significant digit is just 10 microvolts. While the X-Tech already has the special function that we can get to 500,000 counts, and then we get one extra digit going down to 1 microvolt. Now you might say, well, what is it good for to have 1 microvolt resolution? The answer is simply if you're observing drift in a measured voltage. For example, at some point of your circuit there is a strange behavior and you just want to observe if it is drifting with temperature or with any other control voltage that you change, then 1 microvolt resolution can be quite handy. Or there are, for example, sensors or voltage sources which give out such low voltages, like for example thermocouples, that you simply need this 1 microvolt resolution. And remember, resolution has nothing to do with the accuracy. I will not talk in this video series about the accuracy in the different modes. You all of them are better than anything that you really need in real day life, and you usually can trust the specifications you get from the manufacturer in case it's a reputable manufacturer, and most multimeters are an order of magnitude more accurate than the worst case specifications they give. So, and the EV block 121GW also has 1 microvolts resolution. So that's the lower end. The higher end is usually limited by the safety rating of the multimeter. For example, here the highest rate would be, from the measurement display, would be 2000 volts, but they only state it as 1000 volts, simply because this multimeter is only rated for 1000 volts DC. And there are similar maximum ratings here for the other two ones. So the upper range is not so important. By the way, if you want to or have to measure voltages that are above the safety rating of your multimeter, just build yourself a voltage divider with a high voltage qualified resistor or 2 resistors, and then you can also measure in the kilovolts range if you really have the courage to do that. So to demonstrate the peak capture function, we will try this with a 9-volt battery, but because we don't clip our probes to the pins as we would do perhaps in a circuit where we want to capture a minimum or maximum voltage, we will get higher voltages than the battery really has. Let's measure it. It has 9.6 volts, simply because you always have some volts here just floating around in the air, and that adds up at the moment, or can add up at the moment of contacting the battery. And this mode has of course reduced accuracy, but that's not the point. The point is, if we go now into peak mode, that it registers the maximum voltage, and if we reverse it, it should also record the minimum. It displays at the moment the maximum, but now you can cycle through maximum. Minimum is minus 9.79, and the difference between them, max minus 19.57 volts. So that's a very useful function to capture any glitches or intermittent error voltages or currents in your circuit under test. And this has nothing to do with the hold function. To be honest, in all of my life, I've never used the hold function. Here at the old Metex, there is only a hold switch. So the idea of a hold function is just you're probing and cannot see, cannot take a look at the multimeter. But when you're probing and have to look at your circuit, you just don't have, quite often you don't have a hands free to push the hold button. So the auto capture function is much more useful than the hold function. Of course, here this multimeter also has a hold function, but as I told you, I never used it. And a bit related to the peak capture function is the max and minimum function. That is, you're probing a voltage for some time, and the multimeter will automatically register the maximum and minimum measured voltage or current during that measurement period, and you can later cycle through the maximum, the minimum, and again the difference between maximum and minimum. So 2 quite useful functions just to find and to record intermittent errors or finding maximum and minimum values. And the EV block is quite similar to that, but I've noticed just that the 1 millisecond peak function, which is nearly identical to the peak capture here, it just doesn't work, or I'm too stupid to make it work. If I press the button, there should be a 1 millisecond annunciator in the LCD, but I hear it beeping, but I can't get this to work. So perhaps somebody can help me, and perhaps there's a new firmware update where this function is made working. Similar to that is the auto hold function. That is, if we have the traditional hold button, just as here the switch and here the hold, and then if we press one more, we get the A in front of the auto. And so, if we take our battery, it will just register the voltage when it detects a stable measurement. So let's touch the battery terminal now. and you could hear around after 1 or 2 seconds. Then it made a beep, and then it registered the voltage and holds it now automatically. So this is also quite useful. So these functions, the peak capture functions, the maximum and minimum in a time interval. Here you also have not only maximum and minimum, but also you can measure the average in a time interval. So these are quite useful in doing repair work or searching for glitches, faulty circuits that behave strangely, etc. And none of that was available during the time when this older multimeter was produced. So there's one final thing you should know about when you're measuring voltages, and that is the input impedance of your multimeter. Impedance is in this case the same as the input resistance, which is traditionally 10 megohms, and we can try this out by simply interconnecting the multimeters. Let's see if we can really measure the 10 megohms. We're going to, and you can see here it's 10 point something, a little bit going down. So this is 10 megohms. Now we reverse this and go here into ohms measurement mode. And we measure again the 10 megohm input resistance, and the same will be certainly the case with the EEV block. So all of them have 10 megohm input resistance or input impedance. Here we are 10 going down. Well, it's 11 point something. Anyway, these 10 megohms, as high as it sounds, could in fact be too much of a load if you're measuring certain sensors like photodiodes or any other high impedance voltage sources. Then 10 megohms could be too high. I've encountered twice or 3 times a situation where I needed at least 100 megohm, better 1 gigohm. And that is in some higher end multimeters called the high Z mode. Then the input resistor divider, where the different ranges are realized with, is simply bypassed, and your voltage goes directly to the ADC without any input resistor divider. And the ADC usually has CMOS inputs, which, as you know, has input resistance or impedance in the range of a gigohm. And by chance, I discovered in a cheap multimeter that we have here at our workplaces that in fact it does have a high impedance mode, which is not mentioned in the manual. And that is this cheap Unity UT139C. I've made already some time ago a video about the high impedance mode of this thing, but let's verify this again. Just in the normal volts mode, we're getting our 10 or 11 megohm input impedance. But if we go into the millivolts range or mode, then it shows overload, which means it's at least larger than 50 megohm. And I've verified this with a gigohm meter that I have at home, that the input impedance is in fact larger than 1 gigohm. So obviously here in the millivolts range, the input signal is directly routed to the ADC. I can only speculate why they didn't realize a high Z mode here in this higher end hobbyists multimeters. Perhaps it's either protection of the multimeter, because if you go directly to the input of the ADC, that could be easily destroyed by overvoltages, or perhaps you lose the CAT rating because you're not only bypassing the input resistance divider, but then perhaps also some of the protection elements. Okay, so far, and it's quite useful to have at least one multimeter with a high Z, high impedance voltage measurement range. So, and if you've looked closely, you might have already discovered here a marking on the range switch which says low Z, which is the opposite of high Z. So what is that good for? Well, if you're in the AC mode, and you will know this, that you never get a zero display, but you're always measuring some ghost voltages, which are simply coupled into your test leads capacitively or inductively by the omnipresent 50 or 60 Hertz line frequency. And so you have electromagnetic fields all around. And now you imagine you're working in an environment with high current or high power machines or motors or power plants. Then the electromagnetic fields generated by that could give you ghost voltages of several volts, perhaps even tens or hundreds of volts, which are basically not real. And how do you counteract this? Well, you just short out at least the capacitive coupling by going into low impedance mode. Here, this is around 2 kilo ohms, and all ghost voltages are simply eliminated by this low impedance. Of course, this is only useful when measuring signals from line sources, and this mode is basically useful for electricians or if you really work near high power machines, power sources, etc. I never encountered a situation where I really would have needed that, but in case, you never know. Anyway, here you have this mode, but basically only for AC voltages, and with reduced sensitivity you only get a resolution of 0.1 volts, but that is enough for this situation where you need this. So that is basically all there is to say about voltage measurement, except for one thing, and that is AC measurement. So now I've put all three voltage inputs of the three multimeters in parallel, set them to AC mode, and at the moment I'm having at the input a 1 volt AC signal of 50 Hertz. Here the dual display of the EV block multimeter is quite nice. You can see 49.99 Hertz. So in fact it's 50 Hertz. And you can see the display is basically the same. The accuracy of any multimeter is greatly reduced in AC mode, so you cannot expect the same accuracy as in DC mode. So basically all are displaying the same results within a few tenths of a percent. Now, first experiment, let's rise up the frequency in steps of 10. I'm sorry I can't show you the function generator in parallel, but you just have to trust me that I'm now going to 500 Hertz, and you can see already here the 500 Hertz of 499.9, and basically the display remains the same. Now let's go up to 5 kilohertz, and we can see some slight changes here, but this is still within the given accuracy of the multimeter, and you can read here 4.999 kilohertz. So another step of 10, 50 kilohertz. And now here the good old METEX starts to give wrong results. We're already 13% out of the correct value, while these two more modern ones hold up. Another factor of 10, 500 kilohertz. And we get still the right frequency displayed, but you see the displayed value drops down nearly to zero. So obviously we are over the cutoff frequency of this multimeter, while the X-Tag is still giving a halfway decent result, 10% off. So the cutoff frequency of the X-Tag is, at least in this range, a bit better than with the EV block, while the good old METEX has completely dropped nearly to zero. So first you should know that you cannot expect correct results up to arbitrary frequencies. You can be lucky if your multimeters goes up to 100 kilohertz. Let's try this one, 100 kilohertz. And you can see here we're already 35% off, while the two modern ones are still with 100 kilohertz, still giving a correct result. But now let's change. Let's go back to 50 Hertz, and now let's change from a sine wave to a square wave. and the square wave in fact has now 1.41 volts would be the correct result, with the same peak amplitude that we had with the sine wave. So we're basically having the same amplitude, but now a different shape of our signal, changing from a sine wave to a square wave. And you can see the METEX is already very far off the true value. And that is the advantage between a so-called averaging multimeter, which is the old style or old type how to measure AC. With averaging multimeters in the AC mode, you can only correctly measure sine waves. There are correction factors for other waveforms if you know their shape. So we could also change to, let's say, a triangle wave. And they are now more near together again with their displayed values. But with the square wave, you can see this one is far out from the correct value. And I've made a whole video series about true RMS measurement, what you all have to watch out for there and what it all means. For beginners, you just have to know only true RMS multimeters, which you can read here, true RMS. And here it's also true RMS. Only they give the correct value for waveforms other than sine signals. And now we go again one step back to our sine signal, and we're now adding an offset of 1 volt. And first of all, you can see basically nothing has changed, although the waveform is now a kind of upward shifted sine wave. And now comes the important thing. These two multimeters have a mode that is called True-RMS AC+DC, and that is important whenever you have an offset in your voltage, a DC offset. And now let's change to AC plus DC measurement. It's a little bit different in the two multimeters here. I have to go to the range switch, and here I'm changing the mode, and perhaps you can read it, DC plus AC. And these two now display the correct value of a sine wave with a 1 volt DC offset, and they are even within the least significant digit, nearly equal. While this one remains at 1 volt. I can increase the offset, let's say, to 2 volt. And you see nothing changes here. But the two better ones with true RMS AC plus DC, they recognize this DC offset and give the correct result. So if you want to delve deeper into this topic, what is true RMS, and especially what's the advantage, the mandatory advantage of true RMS AC plus DC, I will put a link to the 3 or 4 part video series about this very important topic down in the video description. To sum it up, only a multimeter with true RMS AC plus DC capability is really of a good use. In theory, again, you could, when you know that you're having a DC offset, we can just change to DC mode to see the DC offset. Now we're in DC, and we can see, I told you, we have 2 volts DC offset, and we get exactly that displayed. And here we get the same 2.035 volts DC offset. While here we could also go to DC measurement, and we get the same result, so this is correct. So now if you would know the shape of your waveform and you measure separately the DC voltage and then the AC voltage, you could with all 3 of them in theory calculate the true RMS AC plus DC value. But who does that? I mean, if you have a good multimeter, you want to get it directly on the display, and that is just accomplished. With the true RMS AC plus DC measurement mode. while it's hopeless here with these old averaging multimeters, then you would need an oscilloscope, and if you have a modern digital oscilloscope, that can also display the calculated True-RMS AC+DC value on the screen, and that up to the highest measurement frequencies, while these are limited to around 100 kilohertz, a little bit depending on the frequency range, or the cutoff frequency goes down the lower your measured voltage is. So if you go into the millivolts range, the cutoff voltage will probably be much lower than 100 kilohertz. But anyway, if you want to know more about this topic, watch the video series about True-RMS AC+DC measurement. So that was all I can think of about voltage measurement, and now let's go finally to what's important in amps measurement. So we already dealt in the first part of the video series about the limitations of the high amps measurement. This one here, for example, unfused up to 20 amps. The other two are 10 amps fused maximum current. What you should have to know there, just consult the manual. If you go to the maximum current of, let's say here, 10 amps, you may only have such high currents for a few seconds, simply because the shunt resistor used to measure these high currents starts to warm up, and not only by the warming up changes its resistance and gives less and less precise results, but the heating up could finally lead to that it burns through, and there is even a time of several minutes that you have to let it cool down. So when we go to the lower ranges, then of course the resolution becomes important, and you can also see here are the steps that you can select are not a factor of 10 but a factor of 100, because just they didn't have enough switch positions. And here in the lowest range, 200 microamps, the resolution is 10 nanoamps. Let's see what we get with the X-Tech. It's also 10 nanoamps. And with the EV block multimeter, we initially also have 10 nanoamps. You can see 0.00, so the last digit is 10 nanoamps. But we can switch an additional times 10 amplifier in, and then we get 1 nanoamp resolution, but we get an additional offset. That's just the op-amp offset. But we can, of course, that's another good use of the relative button, we can subtract this out. So this has 10 times higher resolution, and sometimes you need nanoamps resolution. If you want to go into the picoamps range, you need a special purpose pico or femtoamps external amplifier, but 1 nanoamps resolution is already quite good. But there's one additional thing you have to know when measuring amps. We had this in the voltage measurement mode, that you strive for the highest possible input impedance for just not loading your source in case you have a high impedance voltage source. And it's exactly the opposite for the amps range. There you want to have the lowest possible shunt resistor, because the shunt resistor of course develops a voltage, and this voltage is just proportional to the current flowing through the shunt resistor according to Ohm's law, of course. But this voltage is kind of stolen from your device under test, so you strive for the lowest possible shunt resistor. But there's of course a limitation. The lower your shunt resistor, the lower the voltage it develops. And we can simply measure the value of the used shunt resistors. And let's start with the X-Tech. Traditional in the high amps range, so the 10 or 20 amps range, it's a 10 milliohms shunt resistor. But let's try to find out what is the shunt resistor used in the milli and microamps range. So we put this one here in the ohms mode, and the X-Tech in the, let's start with the milliamps mode and use the milliamps terminal, and we get 7.2 ohms in the milliamps range. So this is quite a high value already for a shunt resistor. And you can imagine that a 7 ohm resistor can affect your device under test. Now let's go to the MicroAmps range. And there we are at 100 ohms. Or 107. The 7 ohms is probably the resistance of the protection elements, the PTC and the fuse. So 100 ohms is quite a lot. And you just always have to remember that when you're measuring, especially in the low current ranges, microamps, milliamps, that you have in series with your device under test in this case, a 100 ohm resistor. Now let's see what the 121GW gives us if we use the right terminal. And in the milliamps range we get 3 ohms, and in the microvolts region we also get our 100 ohms. The additional 3 ohms is again the resistance of the protection elements. So that would mean that these two are on par. They have basically in the same range the same shunt resistance. But again, we have two features of the 121GW that you don't find very often, or not at all, at other multimeters. First of all, we already saw that in the lowest current range, which we can enter when we disconnect here the ohms measurement, we get 1 nanoamps resolution, but with the same 100 ohms input impedance or shunt resistance, or 103 ohms in that case, because here's an internal times 10 op amp that is switched in when you go to the very lowest current range. And the second is you can read here low burden and here BD off, which means burden voltage measurement off. So burden voltage, that is exactly the voltage that develops on your shunt resistor. And sometimes it's useful to know how large the burden voltage is. So for that purpose we have to go into the, first of all, into the setup mode and change this to burden voltage display on, and then we have to connect with a separate lead the active terminal with the voltage input, and now we should be reading the burden voltage developed over the shunt resistor. But I've tried this with a few different positions here and I can't get this to be displayed, so I don't know what's wrong. Again, I might be too stupid to get this working, and when you change the range it again switches to burden off. Perhaps either there's a newer firmware or I'm doing something wrong. Anyway, I can't get the burden voltage to be displayed. But for today this shall be enough. I hope it was not too confusing, but I think I've dealt with all the important topics concerning continuity, volts, amps, AC and DC measurement. And the rest that remains, which is still quite a lot of features to speak about, for example here the transistor tester, the diode function, capacity measurement, the Hertz measurement, the duty cycle measurement. There's still a lot of functionalities that you don't recognize at first sight. So anyway, for this time it shall be enough. So thanks for watching. If you liked it, please give it a big thumbs up and see you next time. Bye from Roger. Bye from Kanka Labs.